this experiment we are going to do today is an experiment that consists of 8 variables gotten from female psychiatric patients, and we want to use this data to demonstrate different hypotheses in Stata. The data we have here is actually the age of the female psychiatric patients in age, their IQ, the anxiety level. The anxiety level, we have different levels, about 4 levels of anxiety: none, mild, moderate, and severe. We also have depression. The depression level is 4 levels. We also have another variable here: can you sleep normally? Yes or no. Sex, another variable here: have you lost interest in sex? Yes or no. Then this: have you thought recently about ending your life? Yes or no. And weight increase in weight over the last 6 months. So this is the data collected from these patients, and we're going to use this data to answer the following hypotheses. Now, the hypothesis we have here, or the questions that we may want to address here, is: first of all, do the weight change of women who have recently contemplated suicide differ in any respect from those who have not? So from here, we are going to compare the weight change of the women between the ones that have contemplated suicide and the ones that have not. So the null hypothesis here is there is no significant difference in weight change between women who have thought about ending their life and those who have not. So we are going to use this hypothesis 1 to compare weight change against life, which is people that have thought about ending their life. Then hypothesis number 2 is going to be: what is the association between depression and the suicidal thinking? So the proportion of women who are depressed does not differ significantly between suicidal and non-suicidal women. That is, women who have thought about ending their life. So we are going to compare depression and life. So let me start by saying, or going back to the first hypothesis. Now, the first thing I'm going to do, I will go over to Stata, and I will upload my data into the Stata, and we are going to see how we analyze weight against life. And here we see that weight is a continuous variable and the life is a nominal variable. So we are going to compare weight against life in the first hypothesis. So let me switch over to Stata so that we can upload our Now, this is our Stata. I've already uploaded this file to the editor. We have already uploaded the file to the editor. So if I want to do the upload again, I'm going to have, if I go to File, I will see Import. I will go to Excel spreadsheets. I will browse I will get to where my file is, and the file is here. So I will make sure that the heading import first row as variable name. I'm going to check this so that my first row is going to be variable name. I will click OK. So data in memory have changed. Do you want to continue and use unsaved data? So what it means that is that this is our data here. So our data has been uploaded. Now, if we want to compare, okay, before we do that, we are going to, if you look at the data here, you will see that our data here, the categorical variable, anxiety is a categorical variable. We also have 999 here. You can see that we need to convert this 999 here is a missing value. These are missing values. So we are first of all going to convert these missing values or this 999 into a recognizable missing value, which is dots. So to do that, I'm going to switch over to so I'm going to type this command here, mv decode. I'm going to type this command, mv decode underscore all, comma, mv minus 99.
We can see, excuse sir, we can see where you're typing.
Eh?
We can see where you're typing from.
Look at where I'm typing at the command window here.
So,
Are you not seeing my Stata interface?
I'm seeing the interface, but I can't see you typing.
Look at where I'm typing at the downside of the command bar here.
Okay.
Look at where my is at the command bar here. So here now I'm going to type mv decode underscore all, comma, space, mv into minus 99. Now what it means now is that I'm going to convert all those numbers that are minus 99 here are just placeholders. Instead of me to leave this place open, I will just put minus 99 in the cell, meaning that those things are missing values. So now I'm going to tell Stata that this minus 99 is a missing value. So that's why I wrote this. It will now convert it to, it will now recognize it as a missing value so that it will not
what is the full meaning? What is the full meaning of that MV? Hello, sir. Hello, sir.
Hello, missing value.
What's the full meaning of MV?
MV, missing value.
Okay.
That is decode a missing value. That's what MV decode. Are you there? MV decode underscore all, comma, space, MV.
It's okay.
Yes. So you now.
It's okay.
Command MV decode all is not recognized. Okay. So let me say MV decode space all, comma, MV into minus 99. MV decode of comma space 2 minus. Okay, so you see when you type this value, it will go to all those places where you have minus 99 and convert them to missing value. So you see under IQ, we have minus 99 occurred 2 times here. In anxiety, minus 99 occur 1 time. Sleep, minus 99 occur once. Sex, minus 99 occur twice. So it has converted all. That's why you see this all here. Means everywhere in the data where you have the minus 99, it will be converted to missing value. So if I go back now and check, you see that all the minus 99 is now dots. All the minus 99 is now dots. So this is how Stata.
Excuse me, sir. What if you did that from your Excel even before now?
No. You have to, if you do the dots there, it will not see it as a missing value. So you have to do it here and then convert it to missing value using this code here, so that it will recognize it as a missing value. So anytime you have such kind of situation, the best way is to code it in Excel and then upload, then use this command here to convert it to missing value. So after doing that one, now the next thing to do is to convert anxiety to categorical variable. You know, this one is categorical. Depression is also categorical. Sleep is also categorical. Then sex is also categorical. So let's anxiety, we have none, mild, none, mild, and what? Severe. I think so. We have so now we are going to do our label formula. We are going to do our label formula now. So we're going to okay, null, mild, moderate, and severe. Okay, let me run this yes, no first. Sex, life, and sleep. Sex, life, and sleep. So we are going to have label define yn. We are going to use yn as our this thing here, as our code. 1 is no and 2 is yes. So I'm going to, okay. Okay, so now I will now say label values, sex, then yn. I will now do label values sleep. Sleep is yes, no. I will put the yn for all the variable whose option is yes, no. So yn2 will go. Then I'll also do label values. Which other one? Sex.
We've had sex already.
Okay. Okay, we have life. Have you contemplated taking your life? Yn.
Why the choice of yn, sir? Is there any meaning to that?
You can choose anything that makes sense to you. Yn here means yes, no, because our coding is yes or no. So I'm now associating the yn to all the variables that their options are yes, no. So I'm going to create another label now for this what's the other one for
Anxiety.
Anxiety, yes. Anxiety and depression have the same coding, and they are ordinal data. So I can use anything that I like. What will I use now? Let me see. If I decide to use label define, if I say ORD, maybe ordinal data, anything you like, you can use. So ORD, label define ORD, I will now say 1 for none, 2 for mild, 3 for moderate, and 4 for severe.
Excuse me, sir.
Yes.
I noticed that coding in this, what do you call it, Stata. So to every character you code, you must give a space.
Eh?
Could it be that in Stata, every character you code, you must give a space?
Yes, you have to give a space where it is necessary. It's just for you to know when to give space and when not. But you have to give a space for all the distance, for most of them. So here now, I'm going to say label values. Label values. I will now use that ORD now. Label values anxiety. Then I'll put ORD there. I'll say label values. Depression. You have to type it the way it is. You have to type it the way it is in your variable. You can see the thing is capital here. That's why I'm using capital. So because it's case sensitive. So here now, when I go to my data now, you see that all of them have turned to categorical variable. You see? So all the ones that are necessarily turned to categorical variable.
How did you check that?
Eh?
How did you check that?
And you go to your data editor. From data to data editor, you see data here, you go to data editor. To data editor. So you now see all your command have taken effect on the data. So when you close, you are now ready for your analysis right now. So you have been able to do the missing value and also code your labels. So So we can now answer our first hypothesis, which is first hypothesis is that our first hypothesis here say that there is no significant difference between weight change between women who have thought about ending their life and those who have not. So weight change and life, that's what we're going to do in our first hypothesis. And looking at weight change, a continuous variable, and life. Life is what? Life is a categorical variable that has two groups, yes or no. And weight change is a continuous variable. So we are going to use independent sample t-test to do the analysis. We're going to use independent t-test to do the analysis. If you check here, now you see that for the first hypothesis here, the independent sample t-test is used to compare the mean of two groups, yes or no, of life over weight gain of the women. So, do the weight change of women who have recently contemplated suicide differ in any aspect from those who have not? So, to do that, we are going to use independent t-test, and the command here now is t-test weight, by life. T-test weight, by life. So we are going to, if you want to run independent sample t-test, the command is t-test written together. Then weight is a continuous variable, by then the categorical variable. So that's how you run your independent t-test. So let me go back to this, and then
So can we use SPSS to do run this test?
You say what?
Hello, sir.
Yeah, what did you say? Can you go ahead and ask your question?
Hello, sir.
I'm hearing you. Go ahead.
Sir, can we use SPSS to run this test also?
Yes, you can use
Definitely.
SPSS. If you use SPSS, you still get the same you get the same result. So we're going to have t-test weights by life. Now our output here is going to give us the observations that 9 persons said no and 11 persons said yes. And their mean here is, the combined mean here is 6.2, about 20 persons. So the mean difference between people that said yes and people that said no is about 11. So you have a mean difference of 11. Then our p-value here, is 0.0721. P-value is 0.0721. Now what this means is that we are going to, this value is greater than 0.05. And if this value is greater than 0.05, it means that we are going to accept the null hypothesis that there is no significant difference between the mean weight of the women who have contemplated suicide and the ones who have not contemplated suicide. So a p-value of 0.07 is greater than 0.05. So we accept the null hypothesis, sorry. We accept the null hypothesis that there is no significant difference in the weight change between the women who have contemplated on taking their life and the women who have not. So that is for hypothesis 1. I told you that for hypothesis 1, we are using independent sample t-test. If I go to check what hypothesis 2 is talking about. So here now we see that our p-value of this, since this value is greater than 0.05, we accept the null hypothesis that there is no significant difference in weight change between suicidal and the non-suicidal women. So the p-value here is the most important starting for our interpretation. So since this value is greater than 0.05, we are not going to reject the null hypothesis. We accept the null hypothesis. Now the category, the hypothesis 2, our hypothesis 2 here is now suppose we wish to compare the prevalence of depression between suicidal and non-suicidal women. The two categorical variables can be cross-tabulated and the appropriate chi-square statistics calculated using this command here. Now, because we are dealing with two categorical variables, that is why we are going to deploy chi-square, because this hypothesis here is talking about depression and also suicidal women. That means depression and life. This is a categorical variable, and this is also a categorical variable. So the hypothesis here says that the proportion of women who are depressed does not differ significantly between suicidal and non-suicidal women. Which means women who have thought about ending their life, there is no difference in their depression. So after running the analysis, okay, I will go over to Stata to run the analysis. We are going to have the value of 0.03. This 0.03 here means that it is less than 0.05. Oh, okay, let me just go and run the analysis in Stata for us to see how to do it. So when I go to Stata right now, I'm going to So I'm going to see tabulate. Here we are doing cross tabulation now. So you're going to say tabulate life, depression, comma, rho, chi-square. Tabulate life, depression, comma, rho, chi-square. Now when you run that command, cannot tabulate. Okay, I think that's that one should be small letter tabulate. So when you run your tabulation, you're going to have this, which is the cross tabulation between life and depression. Now let me take you over to the PowerPoint and show you the interpretation. So this is the interpretation we have here. As you can see, we have none, mild, and moderate. We have yes, no. So the p-value here, as you can see, our p-value is 0.030, which is less than 0.5. This implies that there is a significant association between depression and suicidal thoughts. There is a significant association between depression and suicidal thinking. For example, you can see that 44% of suicidal women are not depressed at all. As you can see, these are 44% of non-suicidal women. This no here means non-suicidal women. 44% of non-suicidal women are not depressed. So people that have not thought about ending their life, 44% of them are not depressed. Why? Compared to 0% of suicidal women who okay. Then the other one here, we have that 81% of women who have thought about ending their life, people that said yes, 81% of people who have thought about ending their life have mild depression. 81% of women who have thought about ending their life have mild depression. Why 18% of women who have thought about ending their life have moderate depression? So you can see that, and our p-value here say that there is a significant association between depression and suicidal thinking. As you can see, there is a significant p-value here. Let me go further and say, okay, that's for another one. So we have that most people that said yes to suicidal thinking, most of them have mild depression. Most of them have mild depression. And most people that said yes, nobody that said yes that did not have, that fell under none. That means all the people that said yes to suicidal, all of them, none of them were not depressed at all. None of them were not depressed. 0% of all the people that said were not depressed. So you can see that all of them that said yes are depressed. All of them are 81% here have mild depression, while the remaining 18% have moderate depression. So all the ones that said yes basically had one level of depression or the other. So that is the interpretation when you are doing your your report. Now let me go to hypothesis number 3. Hypothesis number 3 is what is the association between sex and the suicidal thinking? What is the association between sex and suicidal thinking? Now, the hypothesis is that the proportion of women who have lost interest in sex does not differ significantly between the population of suicidal and non-suicidal women. So you can also see from here, if you run the same tabulation, because this one is also two categorical variables, sex and life. So you also run the tabulate command in your Stata. Now you are going to see that the people that have lost interest in sex, 71% of those who have lost interest in sex have not thought about ending their life. While 100% of people who have lost interest in sex have actually thought about ending their life. Let me read the interpretation. Those who have thought about ending their life are more likely to have lost interest in sex than those who have not. That is 70% compared to 71%. Those who have thought about ending their life are more likely to have lost interest in sex than those who have not thought about ending their life. So most people that have lost, that have thought about ending their life are more likely to have lost interest in sex than those who have not thought about ending their life. So that is and the p-value here is 0.06, which is greater than 0.05. What it means is that we are going to accept the null hypothesis. We are going to accept the null hypothesis, which means that the proportion of women who have lost interest in sex does not significantly differ between the population of suicidal and non-suicidal women.
Excuse me, sir.
Yes.
But of what sense is this very particular hypothesis that the proportion of women who have lost interest in sex does not differ significantly between the population of suicidal, and then I'm seeing non-suicidal again?
Suicidal and non-suicidal. Suicidal are people that said yes. Non-suicidal are people that said no now.
And so it means it is loss of interest in sex is applicable to both suicidal and non-suicidal women. That's what our result is saying.
Eh?
I mean, based on our interpretation now, our result,
Yes.
are we saying that loss in interest in sex does not differ among the women that have thought about suicide and even those that did not think about suicide?
Yes, with our null hypothesis here now, we can say that we will accept, we are going to accept our null hypothesis. Since our p-value here is 0.06, it means that we accept our null hypothesis. So that's what it means here. That we are not going to reject the null hypothesis. There is no significant difference between the two populations.
See, I'm only trying to read sense into our hypothesis. It is well understood, established that our probability value is significant. Okay, it's insignificant. And so we
accept the null hypothesis. Yes, we accept the null hypothesis here. So let me go to the next one. Now, The hypothesis 4 we have here is between age and IQ. Hypothesis 4 is age against IQ. And because we have two continuous variables now, we are going to use correlation to answer the question. Correlation is used to quantify the strength and direction of a relationship between two continuous variables. So number 4 here, what is the correlation between weight change, age, and IQ? What is the correlation between weight change, age, and IQ? There is no significant correlation between weight change, age, and IQ. So the correlation between the three variables can be found using this command here. Pairwise correlation. That's what PW call pairwise correlation. PW call weight, IQ, age, comma, observation, SIG. Now, let me go to Stata to run
question, sir.
Huh?
Question, sir. Question.
Yes, yes.
Hypothesis 4. What is the correlation? Are you well, can I say, decipher enough to have known that what you are regressing is all continuous data for you to use correlation? Or what if I had used this very particular word, correlation, for two variables that are not actually continuous variable? Would that still warrant me to go and do my test based on the fitness of what I'm looking for?
No, you are choosing your analytical test based on the measurement of your variable. We have continuous variables here, yes. Okay. We have continuous variable here. Weight is continuous variable, age is continuous, IQ is continuous. So you can use correlation to run it.
Don't even start talking of correlation or regression when you know that the variables you are comparing are not continuous variables.
Yes, yes. So let me go over to Stata to run this command here. We have pairwise correlation with IQ and age, comma, observation, SIG. So when you run this command here, you are going to have their correlation. You can see weight against IQ. We have the correlation coefficient of this and a p-value of 0.4. Then IQ against age is minus 0.6343, the p-value of this. Then which other one? Weight against age has a correlation coefficient of 0.2395, and we are going to have a p-value of 0.2 here. Age against weight. This one is IQ against weight. Then we're going to have IQ, age against IQ. for this one. So let me take you to PowerPoint to explain the other ones.
Question, sir.
Yes.
Why pairwise? What do you call it? What about Spearman rank or Pearson correlation? Would it give the same result?
You say?
I said, why this pairwise correlation? Should we use Spearman rank or
No.
what do you call
Pairwise is because we have that's the normal this that one is not based on this one now is this one is Spearman here. Yes, this one is Spearman correlation. That's it. The correlation coefficient here is Spearman correlation coefficient. That's the default for Stata. That's the default for Stata. So when you have, here now we are looking at correlating three variables here. We have three different variables correlating to each other. This one against this one against this one against it. If you correlate weight against IQ, you are going to have this. We are going to have a negative correlation between IQ and weight, minus 0.2037, and a p-value of 0.4, which means that there is no significant correlation between IQ and the age, because the p-value is greater than 0.05. And secondly, there is a negative correlation between IQ and weight. Because of this negative here, there is a negative correlation. That means if weight increase, IQ is going to decrease, and vice versa. So if you come to weight against age is a positive correlation with a coefficient of 0.2985 and a p-value of 0.2, which is not significant. So we can also say that there is no significant correlation between age and IQ. Then we have age against IQ. Sorry, age against IQ right now is going to be minus 0.6343. So what it means here is that there is a significant p-value here, 0.0047. That means age and IQ have a significant correlation, but in a negative direction. That means if age increase, IQ is going to decrease, and vice versa. So that is how the relationship is here. I think I've explained all this here. For the correlation between weight and IQ, that is weight and IQ, correlation coefficient is 0.2 with a p-value of this. The correlation is a weak correlation since 0.2037 is less than 0.3, the threshold for strong correlation. The direction of relationship is a negative relationship since the coefficient is negative. There is no significant correlation since p-value of this is greater than 0.05. So the same can be used to interpret the other ones too. So that's how you can, answer your correlation for these three continuous variables. So it's important to understand that this minus here is very important to determine the direction of the relationship. and also the p-value to see if they are significant. Then this value here, if it is less than 0.03, if it's less than 0.3, it is regarded as a weak correlation between the two variables. Now we have hypothesis 5. Hypothesis 5 here is IQ and depression. Do the intelligence score of women who are depressed differ between the levels of depression? Here, our hypothesis here, there is no significant difference in intelligence score between the levels of depression. Or you can say that depression level does not have a significant effect on intelligence score. Does not have a significant effect on intelligence score. So here now, our depression is a 4-level ordinal category, and our IQ is a considered variable. So because of that, the best test suitable for this situation here is ANOVA. That is why we now deploy ANOVA to answer hypothesis 5. So ANOVA is used to test whether the mean of 2 or more groups differ on a continuous dependent variable. ANOVA can be deployed when you are comparing the categorical variable that has more than 2 groups with a continuous dependent variable. So our
Question, sir. Question.
Okay.
Yes. Is it possible to have as much variables as one can have, or there's any limit to that?
Is it possible to have?
Like, is there limits to the number of variables one should have?
For what?
For the analysis now, for your analysis in your research, like
No,
you're using the number of variables.
There is no limit of the number of variables.
Okay.
There is no limit to number of variables. All you need is to know the two you want to compare each time and know their measurement type, so that you will know the kind of analytical technique you are going to deploy to analyze or to compare the two of them. So here we have 4 levels here, so we can say ANOVA depression IQ, ANOVA depression IQ. So you write. You can also say tabulate depression, summarize IQ. This one you use this command to get your descriptive statistics. This command when you are doing your ANOVA, use this one to get your p-value, and use this one to get your descriptive statistics. So let me go to Stata and then. Sorry. If I say tablet depression, summarize IQ. So it's going to give me the means. It's going to give me the mean. For none, we have 90, 92. For mild, we have 90. For moderate, we have 82 point something. So people that does not have depression have an IQ of 92%. People that have mild have 90. Moderate depression have 82%. So this is the descriptive statistics. So you can now do the ANOVA depression IQ. If you run that, you're not going to have the ANOVA output. So from this observation, now we see that our probability value, look at our p-value here, is what? 0.3832. This value here, our probability value here shows that our the mean does not differ. There is no significant difference in the mean between the levels of depression. There is no significant difference in the levels of depression between the mean. So that's why you see that this is this. So here now we can conclude that there is no significant difference since our p-value is less than 0 point or is greater than 0.05. So that's it here. The p-value here is 0.3832, which is greater. So we accept the null hypothesis that depression level does not have a significant effect on IQ. So the model we have the
Yes, sir.
yes, we have okay, go ahead and ask your question.
Yes, I'm seeing that as the F statistics, or it does not make any difference.
Huh?
The F probability.
Yes,
The probability.
the,
I'm seeing it as the F.
the probability, Abby,
Yes.
that's it now, 0.3832.
No, you didn't get me. I'm seeing it as the F statistics. Is there no any difference?
Which one now? This is the probability. This is
The F there is what I'm emphasizing on, sir.
F. This F here.
Okay, the single F.
Yes, this is the F here. This is the probability of the F. The F statistic here tells how jointly significant the independent variables are in predicting the dependent variable. So the higher the F value, the better the model. So what it means here is that this our F value can increase if our P value is going to decrease. So if our analysis is significant, we are likely to have a higher F value, and our P value can now reduce down to maybe less than 0.05. So as the P value is reducing, the F value is supposed to be going up because that is what determines how significant. If our P value become more significant, that means this value will reduce. Then in that situation, our F value is supposed to be going up. So we also have the R square, which I've already explained to you before, tells me the total variation in the dependent variable that are explained by the independent variable. As you can see here, the mean difference here is not much different, 92, 90, and 82. Telling you that the IQ between the different depression levels are not quite significant, and that is why our p-value is not significant here. So these are the things you will explain in your analysis when you are doing the this, when you are doing your report. So we are going to have regression analysis here. We are going to have regression analysis here. Okay. So here now, what is the relationship between age and IQ? There is no significant relationship between age and IQ. So what it means here is that we are going to have to predict age if we know the IN, to predict IQ if we know the age. A simple linear regression is used to model the relationship between the dependent variable y and a single explanatory variable. So here we are going to have examine whether age predicts the IQ of a psychiatric woman. So we have age here being the X and IQ being the Y. Dependent variable is IQ, and we can predict using age. So when we know the age of a psychiatric woman, we can now predict her IQ. See that our regression equation is stated here, and we are going to deploy this thing. Now you see that IQ, we want to predict the value of the woman's IQ when we know their age. Age is the independent variable predictor on the x-axis, while IQ is a dependent variable response variable on the y-axis. So the null hypothesis here said that there is no significant supported relationship between age and IQ. So the command here in Stata is regress IQ and age. In this case, now you are going to put IQ, the dependent variable, first. You are regressing IQ against age. Regress IQ, you must put the dependent variable first after the regress. That's very important so that it will know that the IQ is a dependent variable. If you are doing multiple regression, you can now list all the independent variable after the dependent variable. You can list all the other one, but here is only age. So if I do that analysis, I'm going to have this output here. If I go to Stata and let me go to Stata and do the analysis, I'm going to have it as is. So I will say regress IQ and age. So if I do that, I'm going to have this output here. So let me take you to PowerPoint and display. So here we have our first table here. So okay, this table here we have our coefficients. The coefficient table here we have age, and this is our constants. So you see that age against IQ here, we have minus 0.47 as our coefficient. Minus 0.47 is 26. And a constant, our constant is 108. Constant. So the regression coefficient, which is equivalent to B in the equation, is minus 0.48. Means that 1 year increase in age. It means that 1 year increase in age will result to 0.47826 units decrease in IQ of the women. So there is an inverse relationship between age and IQ. As the age increases, IQ is going to be decreasing. The negative value indicates the direction of the relationship. Means if age increases, IQ also decreases. So if p-value of 0.000, as we can see here, 0.000, which is less than the significant, indicate that there is a supported relationship between age and IQ, meaning that age has a significant effect on IQ. We reject the null hypothesis. So from here, you see that the coefficient here is the estimate of the independent variable and the constant. It compares the estimate of the intercept and the slope, the sign. So the sign of the coefficient also tells the direction of the relationship. The standard error shows the deviation of the coefficients. It tells you how much deviation that occurred from predicting the slope of the model. So we also have our p-value. The p-value here is less than 0 points. Okay, where is it? Our p-value is, yes, our p-value is less than 0.05, which is quite significant. So here we conclude that age has a significant effect on IQ. Age has a significant effect on IQ. So that's all this analysis here depends on the type of data you have, what you are comparing. So what is important here is to know the type of data you are working with and the suitable analytical procedure that you can use to analyze it. So this class now has reviewed all the 5 hypotheses and be able to tell us the appropriate, if this is your data now and you have 5 hypotheses, you can use different tests to run all of them and get your answer. Just make sure you know the type of data you have for each of the type of variable data you have for each of your variables. And once you know that, then you now know the kind of variable you can, the kind of analytical procedure you can use for the data you have. Then you can easily make your choice.